All right, welcome everyone. It's great to have so many attendees here with us today. My name is Lukas Mosser. I'm the Head of Research and Development in Earth Science Analytics. And in the next 25 minutes or so, we will be looking at the value of machine learning in geoscientific predictions based on a practical example that I'll walk you through. So the challenge that we face specifically in the subsurface is that many of the relationships that we have in our subsurface data sets are complex relationships that are difficult to model analytically. It's difficult to derive mathematical relationships between our observations and the properties that we wish to predict or infer from the data. The solution that we're going to propose here today is that we use validated data-driven machine learning models to actually make those predictions from the observations that are available to us. Some of the challenges that we have to overcome are going to be that we're dealing with high-dimensional data, which is difficult to visualize. We're dealing with sparse data sets, which often come with trends and strong heterogeneity or noise. And of course, we want to be able to benchmark our solutions and to define when our models are actually doing a good job and when they're useful for making predictions on unseen data. So what we will cover in this webinar is we're going to look at when machine learning can actually help us make better predictions, what our data can tell us about our underlying features, and how we might choose a good model. We will also look at how we can actually measure the performance of these models and ultimately define how these models will perform on unseen data that we have not acquired yet. And finally, and most importantly, we of course want to build confidence and trust in our modeling efforts, and I'll show you an example of how we can do that. So just as a disclaimer, the material and presentation that I'm showing today does not represent an exhaustive workflow. There's many more things that we can do. It's meant to be almost like a tutorial on some of the fundamental concepts around machine learning and the important steps that you have to take to be able to apply a supervised machine learning workflow. But there's always additional steps and additional work that can be done to further improve the results. And I'll give you some examples as well of how you might go about and doing that. But let's take a step back and look at machine learning in a more general setting. For general audiences, I believe machine learning really has made a huge breakthrough in 2016 when a machine learning system called AlphaGo by Google's DeepMind was able to beat one of the highest rated players in the ancient game of Go in a series of evaluation tournaments. And this is something that has been theorized could potentially not happen in the next 30 years. And here we've had the example that machines today, and specifically machine learning systems today, are already able to beat human players at this very challenging game and can also exceed the performance of human players. There was a beautiful moment in this game where Lee Sedol, the human top-rated player, thought that the machine had made a terrible mistake, but then actually realized that it was a very beautiful move and that he was going to potentially lose the game, which is what I'm showing here on the right-hand side. If you're interested in this specific example, I highly recommend watching the documentary by DeepMind, which goes along with that tournament and the process of how they came about creating the AlphaGo system. But more importantly, maybe for geoscientists and anyone working in the subsurface, geophysicists and surely geologists will appreciate some of the work that has been done by deep learning researchers such as Karas et al. In 2021 around modeling image data. And here specifically, you can see a so-called generative adversarial network, which allows us to create images based on a large training set of natural images that have been gathered. And you can see how these models are able to capture the landscapes, the textures that we see, potentially also in some of the outcrops that we might be interested as a geologist. And it's absolutely fascinating to see how these models are able to capture these details and key features. So, of course, the question is, why are we interested in doing machine learning at all? And there's three main pillars here that we might consider. One is the fact that we might have a problem where we don't actually have any working methods or solutions. And we do know that we have some data available from which we could potentially learn a solution, because we know that there exists a relationship between our features that and our data that we have gathered and the property that we're trying to predict. So here we're actually interested in the ability to make any predictions or to make any to find any solution. The second approach where we might want to apply machine learning is when we already have a solution to an existing problem, which is maybe too time consuming or too computationally intensive to be able to solve it in a practical sense. And we might use machine learning to actually speed up the solution of such a problem. And finally, we might have solutions to a problem, but the quality of those solutions are not good enough, and we want to find solutions which produce better results. And so here we might use machine learning to produce higher quality predictions. So why is machine learning making a comeback as a field? And this has three main reasons. One is on the data side. There are huge incentives for commercial operators to try and make predictions about, for example, the behavior of users. If you go and buy anything online, or which products to show you in a web store, for example, can have an impact on the revenue of these organizations. And so they collect enormous amounts of data that can be used to hopefully make predictions. There's also been a number of benchmark data sets which have been created, which have allowed the academic world to rapidly iterate on the same data sets and try to improve the methods that are available. In terms of the algorithms, there have been advances around algorithms that can learn from very large data sets, such as deep neural networks in the field of deep learning, or methods that allow us to make use of some of the structure that is in our data, such as convolutional neural networks in application to images. More importantly, though, a lot of these implementations are widely available to practitioners today through open source implementations, which allow a wide scale adoption of these techniques for many organizations and individuals. And finally, there's been also an advance in the computing hardware that we have available to actually train these models, which has been democratized through the access of these computing resources in cloud technologies. So practitioners today have the power of what used to be HPC systems available at their fingertips. So you might ask yourself, if you do have a problem that you're trying to solve, whether machine learning could be a good solution for you. And here I have a number of questions that you might ask yourself and see whether machine learning can actually benefit you. The first set of questions is around data. For example, do we know that there is a relationship in the data set that you have available, which you could potentially leverage to make predictions? Or do you have enough data available to be able to make good predictions using any machine learning approach? It might also be unreasonable to acquire labels, or difficult to acquire labels, but if it is possible to acquire good target properties, then you might consider using machine learning. In terms of algorithms, of course, it's always good to check whether there are already good existing mathematical models to perform such a prediction or to create a predictive model. And so if such a method exists, then machine learning might actually not be a good solution, and you might want to go for a mathematical model instead. Then finally, of course, if you want to apply any of these data-driven methods, you have to be able to measure how good these approaches are performing, and you have to be able to define a quantity that tells you how good these models are at solving the task that you're putting them to. And finally, you want to have an implementation or some piece of software that actually allows you to implement these methods together with the necessary computing resources to be able to solve such a task. Now, in the next section of this webinar, I want to walk you through some of these steps and show you some of the important concepts around machine learning that you might consider through a case study that we've done around the Loppahai in the Barents Sea. So the specific area that we're considering here is the so-called Loppahai, where two discoveries have been made in the Alta discovery and the Neiden discovery. This is located north of Norway, south of Svalbard. And specifically here, we're interested in the carbonate formations, the Ørn and the underlying Falk formation, which are potentially interesting prospects for future exploration in this area. There's been a number of wells that have been drilled in these two discoveries. You can see them here on this nice graph, and many of these actually penetrate the massive carbonate Ørn formation and some also the underlying Falk formation. And so what we're actually going to be interested in doing in these upcoming slides and in this case study is that we want to be able to make predictions of the porosities of these carbonates. They are extremely difficult to model as they are controlled by various pore types and textural features. And so they're very tricky for geoscientists to model precisely, specifically given measurements that we might have available from electrical borehole measurements that we acquire on newly drilled wells. So the question here is, can machine learning help us? We have as a given a data set of logs, the gamma ray, the neutron porosity, and the sonic log, together with the core measurements of the porosity. And what we want to find here is a relationship between these three well logs and the target core porosity. This is going to be a functional relationship that allows us to make predictions. And ultimately, we want to answer the question whether we can predict porosities in a new prospect where we might not have acquired any core, but have acquired the same set of well log measurements. So what is the machine learning workflow that we're going to be applying here? Well, the goal is that we want to find a model from a set of training data that allows us to make good predictions, hopefully, on unseen new data. And in general, we can distinguish two phases for this workflow. The first phase is the model training phase, where we're going to combine our training set, which consists of the well log measurements together with the core data, the core porosities. We're going to inject that into a so-called machine learning algorithm. And the machine learning algorithm consists of everything that we need to create an actual model. It consists of all the pre-processing steps and cleaning steps for our data. It consists of tuning and optimizing the parameters of our functional relationship, which is going to be our model. And then we also might have some post-processing of the results. Ultimately, this combination of the training data set and the machine learning algorithm gives us one realization of a machine learning model. And in the second phase, when we actually want to go and make predictions, we can inject new data, which we potentially have acquired when we drilled an additional well, and we can use our machine learning model to make predictions. So the data set that we have available here is a set of core porosities from the Ørn and the Falk formation. You can see here a visualization of the porosities versus the measured depth along the four wells that we're considering here. And additionally, I'm also already showing here a nice graphical visualization of the carbonate porosities that have been measured in these four wells. And here we can already get a feeling for the similarity between the wells and the porosities measured in these penetrated formations. We can see, for example, here the 11.4 and 11.4a wells. One of them is a sidetrack of the other. You can see that there's a high similarity in terms of the distribution of the porosities at this well. And so here, in general, what we will have is the gamma ray, the sonic log, the neutron porosity, and we're going to try and predict the core porosity from these three input well log measurements. But before we do any machine learning, most importantly, we actually have to go and look at our data. And we're going to use here a concept called exploratory data analysis, or EDA, which is an approach that allows us to summarize the characteristics of our data using statistical methods and also graphical representations. The main objectives of EDA is that we might suggest hypotheses about the underlying causes of the observed phenomena, for example, which factors might influence carbonate porosities, or determine which features correlate well with the target property here, the porosities that we're trying to model. We also have to figure out whether all of these data sets and along these wells actually follow a similar distribution, or if they are potentially correlated in space. And then finally, we might make some suggestions about which data we might want to acquire in the future. If we see that we have some missing data in some of these data sets, we potentially might go back and acquire additional data to try and improve our modeling approaches in general. So let's apply this, this concept of exploratory data analysis. And we typically start off with just summarizing our data in terms of a few summary statistics. Here we're going to consider a total of 824 data points. So we have 824 core porosity measurements together with the corresponding well log measurements. And the average core porosity is 9% with a standard deviation of 5%. Here on the bottom, I'm now showing univariate feature representations as histograms, where the three columns represent the three input features to our model later on, the sonic log, the gamma ray, and the neutron porosity. And in rows, we can see here always a comparison of the four wells that we're considering. And already here, we can observe some differences or similarities between the data sets. This is conceptually important to make sure that we don't have any outliers in our data. And if you have a watchful eye, you can already see that potentially the first well that we have in our data set here has some features that are not similar to the other three wells. So here I just want to have you keep that in mind for the later stages of the modeling process we're going to go through. In addition to looking at just individual features, we can also consider pairs of features, or so-called bivariate statistics. And these we can also represent nicely in a visual form. Here on the left side, we might consider showing a scatter matrix, which on the diagonal just has the histograms of the individual features that we can see as rows in the matrix. And then as rows on the off diagonal, we can see pair plots as scatter plots between the target property and the input feature, where we can already see that there are potentially some weak relationships between the neutron porosity and the sonic log with the target core porosity that we might have. This can also be visually represented by a so-called correlation matrix, which just shows us the same information about correlation of these features in a visual way. Here we can see that there's a weakly positive correlation between the neutron and the sonic with the porosity, and a weak negative correlation between the gamma ray and the target porosity. So when we go and do any modeling, of course, we want to be able to tell whether our model is doing any good. And the way that we quantitatively estimate that is through something that we call a metric. A metric should really reflect any of the goals that we have in our modeling effort. This can be just purely the error that we might make, and we're going to here use the so-called R-square factor to put that as a quantity for a metric, but it can also include other things like, for example, how fast you're able to make predictions. You might consider that as a metric when, for example, you have real-time data that you want to be able to predict. And making predictions in real time, of course, requires models that are able to meet the standards necessary to provide fast enough predictions. And so you could incorporate that as an additional metric in your set of metrics that you observe for any model. Here, we're going to use the R-squared, which is a measure that's going to tell us how much better our model is going to do compared against just using the average core porosity for making any prediction. And so if we make perfect predictions on any unseen data, then this value will be 1. And if the value is 0, then actually we're not doing any better than using just the mean value for porosity. And if it's a negative value, then we're actually doing worse than just the mean. So we do want to end up in a range of between 0 and 1. Now, opposed to a metric, we also consider how we're going to actually train our model on any data. And for this, we're going to use an objective function or a loss function. This is essentially what we use to minimize the mismatch between our observations on the training set, given the predictions from our model and its weights. And we're going to optimize the weights so that we minimize the objective function. So for this example, we're going to use a very simple model, a linear relationship between the input well log measurements and target core porosity. You can see each of these well log measurements comes with an additional weight that is assigned, which we're going to infer from the training data set. You can think of this relationship as the function of all the possible linear relationships between the gamma ray, the sonic, and the neutron together to make predictions about the porosity. But we're going to choose one specific instance of these weights that will realize one specific function to make these predictions, which is going to minimize the objective function on the training data set. And fitting this model on the training data by minimizing this mismatch is actually what we call learning from data, or solving a learning problem. Of course, we're going to have to evaluate, in addition to that, how good such a model actually performs on held out data which it has not seen, to be able to judge the performance of such a model. The way that we're going to do that is that we have all our available data initially grouped into one big bin, and we're going to split that data into two parts. We're going to create what's called the training data set, which we've already discussed, which allows us to, together with the machine learning algorithm, obtain a machine learning model. But we're going to have a second data set, the so-called test data set, which we can subsequently use to actually compute our metrics and see how good our model performs on unseen data. And this will give us a measure of the model performance of this specific model that we've trained on our training data. The final model that we're actually going to obtain is that we're going to recombine the training set and the test set, and we're going to fit that model using our machine learning algorithm to get us our machine learning model, and then we can use that specific instance that has been trained on all the data we have available to make predictions on unseen data. The assumption here is that, of course, when we make such predictions, that the model hopefully performs up to our estimate of our model performance that we obtained in the previous step, and hopefully also a bit better because we've added some additional data to the training data set. So let's do this for this specific example and find our model. The way that we're going to perform this is that we're going to create a number of splits, and we're going to differentiate these splits based on each of the wells. So we're going to hold out one well at a time, where we train on the wells that are shown here in blue, and we're going to make a prediction as if we didn't acquire any data at the well that is shown here in red, and measure the performance metric on the held out well. And we do that holding out one well at a time, which leads us to these 4 individual splits. And we can see that for some of these splits, the performance is quite good. It's higher than 0. But for one of these, it's actually quite poor. It's minus 0.45 test performance. And if we look at the average test performance, so taking the average test splits performance, we get something that is slightly less than 0 as well. But having such a negative performance is always good to go back and investigate why this might be the case and what might be happening here. So we can now go back to our data set and see what might influence this kind of behavior. So here what we can see, looking back at these univariate feature statistics, and which I already hinted at, is that the input features are quite different. And one of the reasons why that might be the case is that in these formations, we potentially also have other lithologies that might be mixed in with the carbonates. We also have, in addition to that, the potential for having miscalibrated well tops, which would potentially lead to the fact that we're not just looking at the Ern or the Falk formation in this case, but considering something else. And so we could consider here, and this is what we're going to do, to exclude this well, as it doesn't follow the assumptions that we have put into our modeling for the other 3 wells, where we want to make predictions on the Ern formation. So if we do that, and we keep that well out, now we can see that when we look at the average test set performance averaged over the 3 splits that we have available, that we get a positive R-squared factor, and this means that we're already doing better than just using the average core porosity to make any predictions. So this is already great. Now, if we have more complicated models, we might encounter models that don't just use parameters that have to be inferred from the training data, but where also the learning process itself might have parameters. And we call these parameters so-called hyperparameters. Here you can see that the objective function now for this so-called ridge regression model not only consists of the mean squared error, but also in addition to that, a regularization of the weights of the linear model, which is weighted by this lambda factor. And the question here is, how do we find good values for lambda if we can't infer that from the training data alone? One way that we might do that is that we could evaluate just what the impact is of different choices of lambda by sampling this from a grid of values and then evaluating that across a number of values of lambda and seeing what the performance would be. But we have to be quite careful here, because if we just simply optimize lambda on the test data set, then we're going to end up potentially overfitting our test set performance, and this will lead to an overfit model that might not perform well in the future when we apply these models on any unseen or newly drilled wells. So what we're going to be doing here is we're not going to split this data set into two parts, but actually three parts. We're going to have a training data set, which allows us to create a machine learning model, but we're also going to introduce a new data set called the validation data set, which is a subset of all the available data that we have. And on this validation data set, we're going to try and maximize the performance metric by changing this hyperparameter value, in our case, this lambda parameter, and making sure that we find a good value for lambda in terms of this performance metric. Now, in the next step, of course, we want to be able to tell how good is actually such an algorithm with the best hyperparameter selected on any unseen data. And so we're going to bring back our test data set, where we've trained now our model on the training set data, the validation set data, together with the best hyperparameter. This gives us our machine learning model. And if we evaluate now on the test data set, we have our final performance metric, which gives us an estimate of the model performance. So that way we can sort of distinguish between optimizing our hyperparameter and making sure that we don't overfit on the test data set. If we apply this process to this specific example with the ridge regression model and trying to tune the lambda parameter, then we can see that, again, we increase slightly our performance compared to this previous step to around 13% R squared, with a reduced variance also between the different splits that we have available. So up to now, we've learned a number of things. We've used exploratory data analysis to investigate some of the features we have in our data set. We've also realized that there are potential outliers, as we saw during the modeling process and going back into the univariate statistics and the histograms. But we've also learned that it's important to make sure that we don't overfit to our test data set when we have hyperparameters that we want to tune, and that we need to split our data sets into at least three parts if we want to tune hyperparameters and evaluate model performance in the end. Here, we're dealing with a quite small data set, so we've chosen just a very simple regularized linear model to actually perform the modeling for these core porosities. Now, I told you that we have available here the Alta and the Neiden discovery, but it's actually quite interesting because there have been additional wells that have been drilled in this area, which I haven't shown to you. And this is almost like the scenario where we might go out and we've drilled another well, and now we want to apply our model and make predictions. So how good is our model actually going to be at predicting at these new well locations? Before we do any of that prediction, it's always good to go back and look at the data. And here I'm showing you on the top, again, the original training data set that we had with the identified outlier well. And on the bottom, we can see these new additional wells that I'm introducing here. And it's important here just to make sure that these new wells also have some similarities in terms of the input feature distributions that we might expect given the modeling that we've done in the previous step. And we can see that there are quite some differences here in the histograms. And this is just good to keep in our minds. But in this case, of course, we can't do anything about that. We cannot go and acquire a better training data set which might reflect some of these this is something that you might want to do in a further step going beyond the case study that I'm showing you today. So what happens when we actually consider this scenario? Here I'm showing the 4 wells, which you see on the left-hand side. The model has seen all of these data in its final training process. And on the right-hand side, we see these 2 wells as measured depth with the core porosities. When we predict here with the model shown in red, we can see that the model is actually able to capture some of these qualitative behaviors of low and high porosities and changes throughout the wells. And if you consider that potentially we would have not cored in this well, this model would have actually been able to make quite good predictions. If you remember, we had a performance of around 13% R-squared. Here, if we measure the actual blind prediction score, again as an R-squared, we obtain roughly 19% R-squared, which is actually slightly higher than what we estimated through our so-called cross-validation strategy to evaluate the model performance in this case. So this is already quite promising and also qualitatively gives some good results. So what have we covered overall? We've looked at that understanding our data is key to building good models. It's always important to start simple, add complexity in terms of the modeling, then potentially to regularize and also review some of the predictions that you make. We've looked at how we can use cross-validation to estimate generalization performance. And then finally, we've also looked at how we can tune and measure the performance of our models, and that we cannot do that on the same data set. We have to make these at least the 3-way split if we're going to do any hyperparameter tuning. And finally, it's always good to check when you go and apply these models on new data sets whether the underlying distribution of your features actually is similar to what you've trained your model on. There's a number of things we haven't covered, such as feature engineering, looking at more complicated and sophisticated methods from deep learning. We also have not quantified any of our uncertainty that come with the predictions that we have. And ultimately, you might want to make these models available to colleagues and put them into what's called production, or to deploy them in an application and monitor their use in the future. You can do all of this of what I presented today and much more in our platform Earthnet, which has a number of different modules, Earth AI, wells to be able to do all of the machine learning that I showed to you today, Earth View to be able to visualize some of these features that I showed you, and the scatter matrices. And all of this is linked to our Earth Bank, which is our central storage hub for subsurface data, which is OSDU enabled and is available on all of the major cloud platforms.